Hello, today we're going to be looking at graphing relations. So we're talking about Cartesian graphing relations, graphing on a Cartesian coordinate plane. And what we're talking about here mainly is going from the equation to the table to the graph. And we have several things that we're going to be looking at along the way here, including various different characteristics graphs might have. We'll be talking about how to find input and output from graphs, specifically how to find the x and y intercepts. We're going to talk about some things about the shape and direction of the graph, whether it's increasing, decreasing, or constant. We're going to talk about local and global extrema, concavity and inflection points, horizontal and vertical asymptotes, and discontinuities. So we can represent relations in many, many different ways, as we have already seen in some of our earlier videos. And if the relation is between two subsets of real numbers, so real numbers to real numbers, then these are ordered pairs that we can graph in a Cartesian plane. So there's always an equation, or sometimes I'll call it a formula, same thing, a table of ordered pairs, and a graph. All three of these things will exist, perhaps, and we should be able to perhaps go back and forth among the three. But in certain real-world situations, sometimes you'll start with one of these three versions, and sometimes you'll start with one of the others. So just to get us started here, see if you can come up with an example of a real-world situation where you would start by being given an equation. How about a real-world example where you would be given a table, and then one where you'd be given a graph? So think about that just a minute, press pause, and then come back when you've got some ideas. Press pause now. Well, there are actually many examples that you could put here. An equation, computing sales tax, has a formula equation, a process to that. And so that would be an example where we might start with an equation. Many, many examples of that as well. Probably the most common thing would be to start with a table. You go out and collect some data somewhere and then organize that into a table. So, for example, we might go record the daily high temperatures in Fort Smith, Arkansas, the official daily high temperatures. Sometimes you start with a graph, like an EKG or a seismograph or something like that. There are different things that may, the equipment will actually generate the graph to begin with. Now sometimes it's impractical or even impossible to change from one representation to another. For example, in the EKG example, a trained health professional can look at the EKG and say, oh, okay, they know how to interpret just the graph. There's maybe a formula or table that values that would go with that, but there's no need to see that. It's impractical. It's not useful. A trained professional can look at the graph and see what they need to know. Oh, okay, that's a healthy patient. There's a sick patient. Or there's a dead patient. You know, whatever it happens to be. And they can just look at it and tell. In other cases, it's maybe even impossible. For example, the daily high temperature in Fort Smith, we could certainly make a table of that. We could make a graph of it. But there's not really a formula for that one, or if there is, we certainly don't know how to find it, because if we could come up with an equation that would tell us the daily high temperature, we would be able to predict the daily high temperature in the future at all times. Well, that would be nice. Okay, we can make lots of money with that. But that's just too complicated. It's beyond our abilities to do that. We can make sort of short-term forecast, but we have no idea what the temperature is going to be on a certain day, say 10 years from now. But, on the other hand, there are some times that we can start with a relation and start with any one of the three representations, either start with the equation, start with the table, or start with the graph, and obtain the other two representations so that we can get all three representations. So, at least in theory, or at least sometimes in practicality, we can start with one of these three and find the other two. So let's look at a couple of directions where we might do that. So suppose we start with the table. Can we get a graph? So we're talking about ordered pairs of real numbers here. Of course, x and y in this table are the labels for the input and output, and the rest of the things in the table are the actual first and second coordinates lined up in pairs there. So please graph these on graph paper. It's very, very important that you work through these exercises as we do this. So actually get out a piece of graph paper, make yourself a set of axes, label the scale on the axes. So you need to have graph paper. You need to draw the axes. You need to label your numerical scale on the axes so that it makes sense and it can be read. And then locate these points and put dots there and maybe label them as well. Okay, when you're finished with that, come back. Press pause now. Well, here are the points. This is the point, so 3, -1, let's find that. We go 3 on this. Now we need to look at the scale that I have here. So this is, you don't have to label every single thing, but notice you have to label enough of them to know what's going on. So the horizontal axis here, I have the even numbers labeled. So if this is 2, then this would be 1 right here. They're marked off in a half each. And they're marked off in a half each going up, and it looks like a square scale. So here's 3 on the x-axis. Here is -1 on the y-axis, and where those two come together is the point 3, -1. Here is 5, 3. Notice it's on the vertical line here, this purple line, where x equals 5. It's all in this horizontal blue line where y equals 3, and that locates the point 5, 3. And so you can see all of the points there. Just check them out. This is -4, -2. This is -2, -5. That's the last one. 0, 4 is here. 7, 1 will be out here somewhere. There it is. And so forth. So pretty straightforward, not too hard to do that. Students usually don't have too much trouble with that. Now let's kind of go backwards. Let's take a graph. This time it's a graph of an infinite set of points. Okay, and we have a portion of the graph drawn here. And use that graph to complete the table that you see here. So it's the same thing we just did backwards. Okay, now we're going from the graph to the table. Okay, go ahead and finish this out. Press pause now. Okay, so let's see what's happening. We want to see when x is -3, we're going to look at this vertical line right here when x is -3 and see where that crosses the graph, and that's at the point -3, 0, so y is 0 there. -1, that's right here. It looks like that is at -4. Notice that you got to look at the scale here carefully. The x scale goes up by halves, the lines, and the lines on the y scale go up by ones. This is definitely not a square scale. Notice if you go from 0, 0 to 1, 0 to 1, 1 back to 0, -1, this right here is a square, but it's really a rectangle in the way, but not a square in the actual physical shape that you see here. But it represents a square. So this is not a square scale, but that's okay. As long as we have a consistent vertical scale and a consistent horizontal scale, we're good to go. Okay, so when x is 0, that's on the y-axis here. That's right here at -6. X is 1.5, that would be on this line. That looks like it's really close to 8 here. We're going to call it 7.9. You may have to estimate in some cases, but we should be able to estimate at least fairly closely. Okay, when y is 8, 5, 6, 7, 8, that's on this horizontal line right here, and that is about 1.5. Actually, it's maybe actually maybe a little bit to the right of 1.5, maybe 1.5 something, 1.51 or something like that. Rounded off to the nearest tenth, these are correct. So these are almost the same point here. When y is 0, that means it's on the y-axis. Now this time there are 3 places where the graph crosses the y-axis. Here, here, and here. So this actually generates 3 points. -3, 0, -2, 0, and 1, 0 are our ordered pairs. And likewise, it crosses the horizontal line at y equals -5 right here 3 times, and we're going to estimate this one right here at -3.7, and this one right here is negative, let's say 0.8, and this one right here as, let's say, about 0.4. So if we want to go from the equation to the table to the graph, eventually getting from the equation to the graph, it's relatively straightforward to go from table to graph and graph to table. We've just seen how to do that. It's also pretty straightforward and relatively easy to go from the equation to the table to the graph. So we start with the equation or formula. We choose numerous input values, the first coordinates. Especially if it's a function, we're going to choose the first coordinates. If it's a relation that's not a function, we might want to be choosing some of the outputs instead of the inputs at this point. But at least if it's a function, remember the first coordinate is the independent coordinate. That's the one that you get to choose. So we're going to choose a bunch of x values. Write them down in a table. Use the formula or equation to figure out what the corresponding outputs or y values are, and put those in your table as well. Now what do we have? We've got ourselves a table, and we're back to what we just did. So we record those points in the table. We choose an appropriate scale for our graph. We need to pick some graph paper out. We need to label the axes, draw axes on it, label them on graph paper, and then carefully graph these points. It's very important that we use graph paper because we need to get a graph that is precise and accurately able to read off the ordered pairs off of the graph, just like the one we just did, just like the example we just worked on the previous slide. So we can't be sloppy about it. We have to be very precise. And then we've got a bunch of dots graphed. Well, now what do? We connect the dots. Okay, well, be a little careful there because not every dot's supposed to be connected to the next one. But you get the basic idea. If you get enough dots graphed, you've got a pretty good idea what the graph looks like. If there's a portion of the graph you don't really know what it looks like, then graph some more dots in that vicinity and figure out some more ordered pairs. In other words, extend your table a little bit. Okay, so be very careful to plot these points and be sure that you do enough of them so that the shape of the graph is clear. How many points do we need to graph? Oh, if you don't have any idea ahead of time, probably at least a dozen or more. Okay, so let's do an example of this. Let's take y equals 4x, and let's graph this. We're going to make a table and a graph. Okay, and I want you to do this without the aid of any technology at all. Just get a piece of graph paper. You can use a straight edge to draw your axes on there, and then your pencil, and work this out by hand. Make yourself a table on the graph paper somewhere, and then on the grid put your scale, your numerical scale on there. A graph that doesn't have a numerical scale is basically meaningless. It has to have a scale on there. And then plot the points in the correct locations and see if you can figure out what the final shape is going to be, and finish this one out. So go ahead and finish this problem now. Press pause. Actually, let me do this one by hand here, because that's what I've asked you to do. So we have some graph paper here, and we're going to make ourselves a table of x and y, and y equals 4 times x. So I'm going to pick some things, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. Let's keep on going down. 4, 5, 6, I think that's about 12 points or so. And we multiply by 4 to get the output, so that makes this negative 20, negative 16, negative 12, negative 2 times 4, negative 8, negative 4, 0, 4, 8, 12, 16, 20, and 24. Okay, now I want to graph this. Okay, so preferably get a straight edge out. Okay, and get your graph paper up here, and we're going to draw on our graph paper some axes. Let me kind of missed the line there. Let me try that one again. Keep missing the way I'm drawing this. Let's see if I try again. Okay, so we have this, and let's put some kind of scale on here. Maybe I can, go through here, and I could go up by ones, I could go up by twos. Let's say if I go up by twos, so 2, 4, 6, 8, 10. Oh, no, let's just go up by ones. I changed my mind. 1, 2, 3, 4, 5, 6. And you don't have to label every one. You can label every other one or something like that. But you do need to label these. Okay, and let's use a square scale this time. And we can graph some of these points. Now, unfortunately, this is not I'm going to change my color of my pen here. Okay, so we have a dot here at 0, 0, at 1, 4. We also have one at 1, negative 4. And to get the rest of these on here, I need to extend my paper up and down, so I could have used a different scale. Let's go ahead and get one down here because I can extend this down. 3, let's see, negative 2, negative 8, negative 4, negative 5, 6, negative 7, negative 8 would be right there. Okay, well, maybe I need to look at some other points here to get a better idea. So what if I put in a half? Okay, so extend my table out for x and y. If I put in 1/2, when you multiply by 4, you get 2. So 1/2, 2. There's another point. Negative 1/2, negative 2. What if I put in 1/4? Then I get 1. And so forth. Well, eventually I get enough points, I can get a graph and in this case the points are in a straight line, so if you get a straight edge you can draw these in and make the graph look right. Now, notice that there's no guarantee that the points that you have picked over here in this table will necessarily be the same points that will fit in this window. How many points are on this graph? Well, there's actually infinitely many points on this graph. Okay, so can we actually physically list them all out? No. What we can list some representative part of the table. If we need more detail, we can extend our table a little bit. But there's no guarantee that these points will be the same as the ones here. This is not the entire graph either. It goes on forever. Now this arrow here indicates that it does continue on in the same kind of manner, but we can't actually see all those points. But whatever window you're going to draw here, you need to show all of the points in that. Don't go and do something like this and say, okay, well here's a graph and here it is. Okay? No, if this is going to be your window that you're graphing in, you need to show all the way to the edge of the window, and then at the edge of the window, if there's more, you can put an arrow to say, okay, it keeps going. Okay? Also, don't do what I've done here. There's several things wrong with this. One, there's no scale. Number two, it's very sloppy. You know, perhaps that was really supposed to go through the origin, but it really doesn't. Okay? You've got to be able to read points off of this. So I need to be able to look at this and say, oh yeah, that is the point 1, 4, and I need to be able to read it right off of the graph. So it's very important to see that. So here's a computer-generated version of the same function, and I've got a table over here of numerous values. Some are visible in this window and some are not. And then I have a graph here, and some of these points are visible in the table and some are not. And actually it doesn't have the arrows on the end, but it does continue on outside that window. This particular one turns out to be a straight line. But not everything's a straight line. Let's try this one here. Same thing, another exercise just the same as the last one. Take this one, y equals 16 minus x squared. Make a table, again, do it by hand on graph paper very carefully, and make a table and a graph for this one here. Press pause now. Okay, did you get something like this? Hopefully you did. Here's a table with some of the integer values here. Many of these are going to be outside of the window that we have on this. So we might want to go back and put some more detail. So if I only go, oh, what am I going from, like negative 13 or 14 there to about 17 on the y's. So you know, this 0, 16 is going to fit. That's an important point. So we may want to make sure that we get that part of the graph. Okay, because that's a very interesting part of the graph where it turns around there. It's a maximum point. And then we want to get some of these others. So maybe you can see negative 5, negative 9, negative 4, 0, negative 3, 7, negative 2, 12, and negative 1, 15, 0, 16, 1, 15, 2, 12, 3, 7, 4, 0, 5, negative 9. You can see all those points actually here. Some of these others like negative 14, negative 180, they're part of this graph, but they're off of this particular window. And then once you put those dots in there, then we can play connect the dots, and this one is actually connected with a smooth curve. If you're not sure, like what was happening near 0 there, for example, you can look here and say, okay, well maybe I need to plot some more points right here to see what this shape looks like right in here. Then I might graph a half and get a point there, or maybe 1.5, and get some more detail there if I need it. Now, we see that we can take a graph. We're going to look at some different graph characteristics, and of course, as we've already seen, we can read input and output off of a graph. So if we have a graph and we want to find what output corresponds to an input value of 5. So that means we take x equals 5, this vertical line, and see where it crosses the graph. It's this little point right here, and that's 5, negative 9. So the output is negative 9 there. On the other hand, if we're given the output, we're looking at a horizontal line across. Here's one at y equals 7. This purple line that's horizontal going across here, and it crosses at these 2 points, both of which have an output or y coordinate of 7. But then you look and see what their inputs are, and they are negative 3 and 3. So the 2 inputs there that give you that same output are negative 3 and 3. In other words, we have 2 points, negative 3, 7, and 3, 7, and those are points on the graph with that output. So we can look at a graph, and if we know an output, we can find an input. If we know an input, we can find an output. Two places on the graph, if they exist, that we're very interested in a lot of times are specific input-output pairs, or where it crosses the axes. So the horizontal, or x-intercept, or intercepts, if there's more than one, are places where the graph of the relation touches the horizontal, or x-axis. Remember, the x-axis has the formula y equals 0, so x-intercepts are points of the form a, 0. Now, intercepts are not a single number, they're an ordered pair, they're a point. So if I ask for an intercept, you should be giving me an ordered pair. Now, occasionally we'll get lazy and just say, this intercept is a, whatever a is, assuming that the person knows that the y-coordinate is 0. But that's technically not correct. So we really should talk about an intercept as an ordered pair. If it's on the x-axis, the y-coordinate is 0. So that part we know. We want to find the x-coordinate that goes with it, and then we've got the ordered pair. Sometimes we want to just talk about the x-coordinate and not the whole point, and then we call them zeros of that particular relation. So notice what you're doing here is you're letting y be equal to 0, say in the equation or table, and trying to figure out which x or x's go with that particular value. Vertical intercepts, or y-intercepts, are places where the graph of the relation touches the y-axis, and the y-axis has the formula x equals 0, so y-axis or y-intercepts are the points of the form 0, b on the y-axis. Okay, again, y-intercepts are ordered pairs. So when we want to find the y-coordinate of the y-intercept, that's equivalent to letting x be equal to 0, say in the equation, and solving for y. Or let x be 0 in the table and find the y or y's that go with it. Of course, if it's a function, there will only be either 0, none of them, or there will be 1. So look at this particular graph and determine the x and y intercepts. Remember that they're ordered pairs. Go ahead and figure this out now. Okay, well, where are they? The x-intercepts, where it crosses the x-axis here, there's one here at negative 4, so that's negative 4, 0, that point, and one at this point right over here at 4, 0. Y-intercepts are where the graph crosses the y-axis, this purple line, that's right here at the top at 0, 16. Again, the y-intercept, we know the x-coordinate is 0, it's just a matter of finding the y. And x-intercepts, we know the y is 0, we just have to find the x. Now let's talk a little bit about some characteristics graphs have. Let's talk a little bit more about some of the shapes they might have. Now, first we can talk about the direction a graph is going. Is it going up or down or sideways, basically? So specifically, we can call this increasing, decreasing, and constant. So we say that a function f is increasing on an interval a to b if and only if, remember IFF is shorthand for if and only if, c is less than d for c and d in the interval implies that f of c is less than f of d. So c less than d means when we go from c to d, we're increasing x. That means we're going left to right on the graph. And then f of c less than f of d says the y's or f's or outputs are getting bigger as we go left to right. So as we increase x, we increase y. Okay, so notice as we move left to right, the graph moves upward. We say that f is an increasing function if any time you move left to right for any c and d in the domain, as you move left and right, c is less than d, then f of c is less than f of d. In other words, as you go left to right, the graph goes up no matter where you are on the graph. That's an increasing function. We say that a function is decreasing on the interval if you still move left to right. So notice when we're talking about increasing, decreasing constant, we always increase x. We always move left to right. The question is, what does y do? Does y go up or down? Okay? And so notice these are functions, so for each x there's only one y. So x is increasing on the interval, of course. Then what does y do? Well, y decreases. So f of c is greater than f of d. Okay. So the f of d is smaller. Okay, as we move to the right, from left to right, so to the right, the graph goes downward. And again, f is a decreasing function if it always moves downward. And then the other thing that's possible is the function could be constant on an interval, and that is, no matter really where you are on the interval, the y values are the same. So as you move left or right, it remains the same. It remains horizontal. So it's a constant function if the y's are always the same, no matter what the input is. So look at this graph. Now this is one graph. I've changed colors, but it's all, consider this all one graph here. It goes kind of up, and here it is. This green part and this blue, dark blue part down here is all one graph. Okay? Where is it increasing, decreasing, and constant? Well, it's increasing. Notice when you start here, as we go left to right, it's going up. And it increases from, well, let's assume that this continues forever to the left in the same manner. So it goes from negative infinity up to negative 2. Notice when I'm talking about increasing, I'm talking about the x values. Which x values make the y values go up. And x's between negative infinity and negative 2 make it go up. And there's also an increasing piece over here from 3 to 4. Okay? It decreases between negative 2 and 3. Notice I didn't say, whatever the y values are here. I said the x values. And then constant from 4 on out, where it's horizontal, from 4 to infinity. Okay, next we're going to define what's called a neighborhood, or an open neighborhood of a point. So we take an ordered pair AB. If you draw a circle around it, the interior of that circle, centered at the point AB, is called a neighborhood. So it's a set of points, so that the distance from those points to that center point AB is less than some distance d, which is the radius of the circle. Okay? So if they're at distance d, they're on the circle, that's not part of the neighborhood. The neighborhood is just the interior of the circle, not the circle itself. So this is kind of an extension of the idea of an open interval, where it does not include boundary points. So a point AB is called a local maximum, or sometimes called a relative maximum, of a relation if and only if there exists some neighborhood so that B, the y value, is greater than or equal to all the second coordinates of the points in the neighborhood. In other words, draw your little circle around the point, look inside the circle. If B is the highest point in that circle, on the inside of the circle, then it's a local maximum. You might have to draw a pretty small circle, okay? But if you can draw a small enough circle so that if there's just one circle where this works, then in fact you get a local maximum. Same idea for a local minimum. A point's a local minimum if you can draw this little circle, this little neighborhood, and in the neighborhood it's the lowest point. Okay, B is the less than or equal to all the second coordinates in there. We call it a global maximum, or if you use the word relative maximum, you'd use the word absolute maximum down here. So global or absolute maximum, if the y value of this point is the biggest y value for the whole thing, no matter what point you are in the domain. And similarly, a global minimum is or absolute minimum is the lowest point in the whole graph. Okay, a couple more definitions. An extremum is either a minimum or a maximum. So if you don't really care, it's just an extreme point. It's an extremum. You don't really care whether it's the highest or lowest. It's just an extremum. Now, extrema is the plural of extremum. Minima is the plural of minimum. And maxima is the plural of maximum. These are kind of Latin plurals here. Extrema are places where the direction changes. So a graph that's increasing and then decreasing, it's increasing up to a point and then decreases after that point, that's going to be a local maximum. And a graph that goes from decreasing to increasing at a point will have a local minimum. So Where are the local and global extrema of this function? Notice it continues on forever on the left with an arrow, but it has an endpoint on the right. Okay, see if you can figure this out now. Well, there is no global minimum because this goes down forever. There is no lowest point. There is, however, a highest point, and it's at this endpoint. So this endpoint is a global and local maximum, and it happens to occur at the point 6, 109. Okay. I actually know the formula that I used to generate this, so I know exactly where it is. Okay. We have another maximum here, but this one's a local maximum. It's not the highest point, period. For example, this point at 6, 109, and even some of these other points are higher. But if we draw a little small circle around this point, it's going to be the highest point. So it's the sort of king of the hill here, top of the thing. So in Mr. Point's neighborhood, he is the highest one, and that one occurs at -2, 45. And this one has a local minimum down here at 3, -80, because if you draw a little circle around it, it is the lowest point in that little circle. If the circle is too big, if it includes some of these points over here way on the left, then it wouldn't be the lowest one. But you can draw a small enough circle so that it is the lowest point, and that makes it a local minimum. A couple other things that we can look at in terms of graph shapes. A graph that's part of a straight line is said to be linear on that interval. A graph that's curved, like part of a right side up bowl, is said to be concave up, and if it's part of an upside down bowl, that's concave down. And if a point where the graph changes concavity, say either from up to down or down to up, that's called an inflection point, or sometimes just a point of inflection. So we can see this illustrated here. So the left part of this graph is concave down. See, this part here is like an upside down bowl. It's increasing concave down up to the maximum, and then it's decreasing concave down till the inflection point. Then from the inflection point on to the right, this part of the graph is concave up. It's like a right side up bowl. It's decreasing concave up from the inflection point to the minimum, and then from the minimum on out, it's increasing concave up. So this one changes from concave down to concave up at the inflection point, which actually happens right here at a half for x. Now, finding inflection points is rather difficult to do. Well, it's not that difficult to do, but it does involve some calculus, which we're not going to do in this course. But anyway, you see that calculus techniques can find that exactly. But looking at the graph, we can tell that there's somewhere in here there's an inflection point where it goes from concave down to concave up. So we should be able to get that inflection point at least approximately in the right place just by looking at the graph. Another characteristic a graph could have is what's called an asymptote. You don't really pronounce the P. It's not asymptote, but just asymptote. A graph that approaches a horizontal line, getting closer and closer to it as it goes to the extreme left or extreme right, is said to have a horizontal asymptote. The line itself is the asymptote, not the graph. The graph approaches that line asymptotically. If it approaches a vertical line getting closer and closer to it, that's called, and the graph itself is getting closer and closer to being vertical, that's called a vertical asymptote. So let's look at an example that has both a vertical and a horizontal asymptote. And one of the simplest examples we can look at of this kind is y equals 1 over x. So let's just look here in the first quadrant. We can graph some points on this. 1, 1. 2, 1/2, 3, 1/3, 4, 1/4, 5, 1/5, 10, 1/10, 20, 1/20, 25, 1/25. I've got some other ones in the table here. 10.1, 100.01, 1000.001. What's happening as we go further and further out to the right? Well, these y values are getting smaller and smaller and smaller, closer and closer and closer and closer to 0. Do they ever actually hit 0? No. So this curve is getting more and more horizontal. At some point, visually we can't tell it apart from a horizontal line, the x-axis. But if we zoomed in close enough, it would actually be a little bit above the x-axis, but getting closer and closer and closer to the x-axis as we go further and further and further to the right. So we would say the limit of this function as we go out to the right is 0, and we'd say that it approaches this line, the x-axis, y equals 0, asymptotically. So this is a horizontal asymptote. The same thing works as you go way out to the left. We have -1, -1, -2, -1/2, -3, -1/3, and so forth. And so as we go out here, they're getting very close to the x-axis. On the way out here to the right, they were a little bit above the x-axis. Way out here to the left, they're a little bit below the x-axis, but again, they're getting closer and closer and closer and closer to it. So y equals 0, the x-axis, is a horizontal asymptote on the far right and also on the far left. Some functions, if they have an asymptote, they have the same one on both ends, some kinds. Other kinds of functions could have an asymptote on one side, but not the other side. So what we're talking about on a horizontal asymptote is what's happening on the extreme right and the extreme left. Now we have a vertical asymptote here as well. Let's look at this. Let's look at our table here. We have 1, 1. What if I put a half? I get half 2, 1/3 3, 1/4 4, 1/5 5, 1/6, 6, and so forth. As we get those x's to get smaller and smaller, like 0.1, 10, 0.01, 100, 0.001, 1,000. What's happening? This thing is going nearly vertical. It's going way, 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 way up there. So as x comes in from the right side, getting closer and closer to 0, the y's are getting bigger and bigger and bigger without bounds. So this line is going more and more like vertical. But notice if I try to put in 0 here, I'm actually dividing by 0. That's not allowed. So we can't have 0 in our table for x because there is no y that goes with it. 0's not in the domain. Turns out 0's not in the range either. The domain and range of this are both the real numbers except for 0. Similarly, if we come in from the left side, when you put in a negative number for x, you get a negative number for y. So that graph is entirely in the third quadrant, whereas the other part is entirely in the first quadrant. So we got first and third quadrants only. No first, no second or third, no second or fourth quadrants, no points on either axis, no x or y intercepts. But we have a vertical asymptote here as well, and you can see that. Okay, so this is an example where we have vertical and horizontal asymptote. A graph that can be drawn over an interval without picking up the pencil, so it's one connected piece, is continuous on that interval. If the domain is one connected interval and the entire graph can be drawn without lifting the pencil, then the graph is a continuous graph. Any place where there's a break of any kind is said to be a discontinuity. So, for example, we have the line y equals 2x is a line, and that's continuous. It's one connected piece. But the graph of 1 over x has a discontinuity when x is 0, and you see the break in the graph there. So this is two pieces. So we come to the end of this lecture. We see by this point you should be able to get what's called a scatter plot of a relation given the table. So if you got a table, you should be able to plot those ordered pairs. Given a relation, given the formula or equation for a relation, you should be able to graph it. You should be able to demonstrate an understanding of some following graph characteristics and identify them on graphs. How do you take a graph and determine input and output values? So if you know an input, find an output. If you know an output, find an input from the graph. If you have specifically, we should be able to find x and y intercepts, maybe using some knowledge of equations, tables, graphs. Talk about increasing, decreasing, and constant, local and global extrema, concavity inflection points, and horizontal and vertical asymptotes, and discontinuities.